In this talk, we will be discussing methods for estimating area-based nitrogen yields and loads to coastal waters with the Stochastic Empirical Loading and Dilution Model SELDM and StreamStats. This presentation was created for the National Coastal and Estuaries Virtual Summit, September 29th through October 1st, 2020. It was prepared by the U.S. Geological Survey in cooperation with the Federal Highway Administration, Office of Project Delivery and Environmental Review. This presentation has 21 slides and will take less than 14 minutes. SELDM is the Stochastic Empirical Loading and Dilution Model. SELDM is a stochastic model because it uses Monte Carlo methods to create a sample of events representing combinations of flows, concentrations, and loads. It's an empirical model because it is based on data and statistics rather than pure theory. It's a loading model because it provides storm and annual loads, and it's a dilution model because it simulates mixing of upstream and runoff loads to indicate the chance of exceeding target values. SELDM was tested and/or reviewed by 43 professionals from the Federal Highway Administration, United States Geological Survey, United States Environmental Protection Agency, United States Fish and Wildlife Service, and 16 state agencies who responded to the call for input and review. The state agencies included 15 state DOTs and 1 regulatory agency. SELDM is a mass balance model. All the components are generated stochastically for each event. This schematic diagram shows a highway bridge over a stream. For each event, the upstream load is the product of the upstream storm flow and concentration. The highway or urban runoff load is the runoff volume times the concentration, which can be modified by stormwater treatment. The downstream flow and loads are the sum of concurrent upstream and runoff values. The downstream concentration for each event is the load divided by the flow. SELDM is designed to produce a population of events representing the combinations of variables that may occur over a 20 to 40 year period. SELDM is a lump parameter model, so it can simulate a literal highway site or a site representing a collection of roads and/or urban areas. The schematic diagram on the left shows the literal highway site draining to a stream with the mass balance components. The schematic diagram on the right shows how contributions of different contributing areas are summed at a downstream site of interest with the mass balance components. In this conceptual approach, the areas are summed and the other hydrologic properties are selected to best represent the net effect of runoff from different areas. SELDM generates precipitation, pre-storm flow, runoff coefficients, and hydrograph timing variables to simulate flow for each event. This schematic diagram shows that each stochastic precipitation event is applied to the upstream basin and the highway site. Each upstream flow is the sum of the stochastic pre-storm flow and the precipitation times the stochastic runoff coefficient value. Each highway or urban runoff flow is the product of the stochastic precipitation and the stochastic runoff coefficient value. These runoff flows may be modified by stochastically generating stormwater BMP treatment variables. The downstream flow for each event is the sum of the component flows. SELDM generates the upstream and runoff concentrations as random, dependent, or transport curve values for each event. The concentrations are simulated from representative water quality statistics. In this case, the measured data are the large white rings and the simulated data are the small white circles. This graph shows concentrations of highway runoff on a logarithmic scale with a probability of exceedance on the horizontal scale. This graph shows how SELDM provides long-term, risk-based water quality information. SELDM provides risk-based event flows, concentrations, and loads with and without stormwater control measures. SELDM also provides risk-based information about long-term annual loads that can be used for total maximum daily load analyses. SELDM generates flow reduction, hydrograph extension, and concentration reduction by BMPs for each event. SELDM does not try to simulate complex physiochemical processes that can vary within and between storm events. What we care about are the flows, concentrations, and loads that enter the receiving waters. This schematic diagram shows the runoff source area as the gray rectangle on the left with the load equation, the statistical black box BMP in the center, and the discharge load equation and receiving water as the blue rectangle on the right. Instead of a complex process-based model for which there is little data, SELDM uses a black box model by using statistical transfer functions derived from stormwater data for thousands of events from hundreds of sites in the International Stormwater BMP database. StreamStats provides access to spatial analytical tools that are useful for water resources planning and management and for engineering and design purposes. The map-based user interface can be used to delineate drainage areas, get basin characteristics, and estimate flow statistics, and much more. Available information varies from state to state. The first step is to enter a location, which can be a geographic name or a latitude-longitude coordinate. Because available information varies from state to state, the next step is to select the state application that is active in the area of interest. The next steps are to zoom in until you see the discretized stream network as a series of squares, press the Delineate button, and then click on a point on the stream. The final step is to get flow statistics and/or basin characteristics. If you click on a stream gauge, shown as the colored triangles on the map, StreamStats will provide links to basin properties, statistics, and available data for each stream gauge. In the following case study, we will use basin characteristics provided by StreamStats to evaluate long-term average runoff loads. We did a case study to look at nitrogen in highway and urban runoff to the Narragansett Bay, which has large, highly developed tributaries in Rhode Island and Massachusetts. This map from the Narragansett Bay Estuary Program shows the bay, watershed boundaries, major tributaries, cities, and major roadways. The color ramp from light brown to dark red indicates the total impervious area, TIA, which is the percentage of impervious surfaces. The color ramp goes from light brown, which is about 3% TIA, to dark red, which is about 47% TIA. We cataloged 50,313 basins above road crossings in southern New England with drainage areas that equal or exceed 0.025 square miles. 3,547 of these basins are in Narragansett Bay tributaries. These box plots show the populations of drainage area, total impervious area, and upstream road crossings in the Narragansett Bay tributaries on logarithmic scales. The triangles show the minimum and maximum values. The whiskers show the first and 99th percentile values. The horizontal line shows the median, and the circle shows the average value. Drainage areas range from 0.025 to 565 square miles with an average of 7.24 and a median of 0.55 square miles. The total impervious percentage ranged from 0 to 83.6% with an average of 16.6 and a median of 12.3%. Upstream road crossings indicate locations where storm flows may enter the stream. Upstream road crossing density ranged from 0 to 106 crossings per square mile with an average of 6.75 and a median of 4.05 crossings per square mile. In this case study, we used the Hunt River as an example. The map on the left is the StreamStats Basin delineation showing the location of the Hunt River on the western side of the bay. Most of the basin lies within North Kingstown and East Greenwich, Rhode Island. At the selected delineation point, the Hunt River has a drainage area of 22.7 square miles, a total impervious area of 15.2%, and 14.14 road crossings per square mile. StreamStats indicates that the percentage of developed urban land from NLCD 2011, which is not shown on a graph, is about 41%. In this example analysis, we used basin properties, which are shown on the table on the left, to estimate the contributing area for highway and urban runoff loads. Our StreamStats application has 4 road categories, which are 1. Interstates and limited access highways, 2. Secondary highways or major connecting roads, 3. Local connecting roads, and 4. Local 2-lane roads. We separated the highway categories, 1 and 2, from the other impervious and developed areas using an estimated width of 50 feet per side for the highways based on Google Earth sampling. These highways cover about 0.23 square miles and are about 1% of the drainage area, 6.7% of the total impervious area, and 2.5% of the developed area. The remaining developed area, which is about 9 square miles, has an estimated impervious fraction of about 36%. Data from the Highway Runoff Database, International BMP Database, IBMPDB, and the National Stormwater Quality Database, NSQD, indicates that urban runoff is enriched in total nitrogen compared to highway runoff. This graph shows the geometric mean total nitrogen concentrations from 13 highway runoff monitoring sites in Massachusetts in comparison to national urban runoff datasets. The median of highway runoff sites is about 1.13 milligrams per liter, whereas the medians of the total nitrogen from separate storm sewers in the International BMP database and the National Stormwater Quality Database sites are about 1.44 and 2.18 milligrams per liter, respectively. The highway runoff is runoff from pavement. The urban runoff also may contain nitrogen from other sources including natural and landscape plant materials, fertilizer, animal waste, and storm flow-induced septic discharges. Although highway concentrations are lower than urban concentrations, yields are higher from 100% impervious highway pavement areas than for the 36% impervious developed areas. The long-term average simulated yields for the highway are 9.67 pounds per acre per year and 5.23 pounds per acre per year with BMP treatment. Long-term average simulated yields are 4.74 pounds per acre per year for the international BMP data and 2.62 pounds per acre per year with BMP treatment. Long-term average simulated yields are 7.52 pounds per acre per year with the National Stormwater Quality Database data and 4.06 pounds per acre per year with BMP treatment. In the Hunt River Basin, highway loads are 3 to 5% of urban loads and about 10% of the difference between urban estimates. This box plot shows the highway and urban loads with and without BMP treatment on a logarithmic scale. Although highway yields are higher than simulated urban yields, the highways cover about 0.23 square miles and the rest of the developed area covers about 9 square miles. The difference in areas explains the difference in annual loads. The simulated long-term average annual load from 10 river basin tributaries to the Narragansett Bay is about 27 tons of total nitrogen from the highways and, if the International BMP database values are used, 675 tons of total nitrogen from other developed areas. This table shows the area of the basins, highways, and other developed areas, the loads from the highways and other developed areas, the sum of these runoff loads, and the percentage of runoff loads comprised of highway runoff. Using these values, highways are about 2% of the developed area and produce about 4% of the loads from developed areas. If the National Stormwater Quality Database values are used, the non-highway developed areas produce about 1,100 tons of total nitrogen, and the highways are about 2.4% of the entire developed area stormwater loads. In conclusion, we found that the Stochastic Empirical Loading and Dilution Model SELDM provides robust planning-level estimates of flows, concentrations, and loads of highway or urban runoff. The StreamStats application, when loaded with data on land covers and the road network, can be used to rapidly quantify basin properties and stream flow statistics. Highway concentrations of total nitrogen from the Highway Runoff database are lower than concentrations from the International BMP database and the National Stormwater Quality Database. Simulated highway yields are higher than developed area yields because the highway is 100% impervious and the developed areas were simulated as being 36% impervious. Simulated highway loads are about 2 to 4% of developed area loads, which is much less than the uncertainty in applicable urban runoff concentrations. You can find out more about SELDM at www.usgs.gov/SELDM. Thanks for watching this virtual presentation. If you have any questions, my contact information is on the USGS SELDM webpage.